Okay, so page 19. Much like how natural log and exponential base e have a way of undoing or canceling each other out, if I have logs and exponentials of the same base, they also can cancel each other out. So, so for instance, if I had e to the x is equal to 12, right? I can take the natural log of both sides, and that's going to end up canceling out because natural log is log base e. So log base e and base e, they are in the same base, and they're inverses of each other. They're going to cancel each other out. So if I have 3 to the x equals 1 over 81, I can take the log of both sides, but it won't be natural log because natural log would be base e. I can take log base 3 of both sides. Much like how natural log and e cancels out, same thing, log base 3 and 3 will cancel out because this is exponential in a log. They both share the same base. I can also bring the x down as well. The x can come down because log properties extends to all logs, not just base e. So if that x comes down, the log base 3 and 3 will cancel out. I'm just left with x equals log base 3 of 1 over 81. If I can somehow rewrite that 81 in terms of base 3, then I can allow for more properties for me to apply. So 81 is 1 over 81 in terms of 3 is what? 81 is 3 to the, 3 to the 4th, and if I bring it up, it's 3 to negative 4, right? So 1 over 81 is 1 over 3 to the 4th, which is equal to 3 to the negative 4. So if I insert 3 to the negative 4 here, then log base 3 of 3, that cancels out. The negative 4 comes down. And I'm just left with negative 4. So if I have an exponential, I can undo the exponential using logs. Likewise, if I have log base 2, I want to undo that log. I can involve an exponent to cancel this property out. So much like how if I have natural log of x minus 4 is equal to 3, if I want to undo that log, that natural log, I can raise both sides with e as the base because I know e and natural log cancel each other out. They're inverses of each other. So I can involve the inverse of log base 2, which is exponential function 2 to the x. So I can raise both sides with 2 as the base. Much like how e and natural log cancels out, exponential function base 2 and log base 2 also cancels each other out. I'm raising both of these as exponents. So that cancels out to be just x equals 2 to the negative 4. And 2 to the negative 4 is same thing as 1 over 2 to the 4th, which is 1 over 16. So
what did you do? Where did you choose them?
So I'm changing this equation to look like this. 2 raised to the log base 2 of x is equal to 2 to the negative 4. I'm raising both sides as exponents.
Also, you can cancel.
So they cancel out, right? So we can take advantage of those nice inverse relationships, just like how we explored with natural log and base e.
Okay, so like for example, like log base 3 of 3, that cancels out.
Exactly. Yeah. So so here are a couple of examples here. Just like how natural log of e to the x is equal to x, and just like how e to the natural log of x is equal to x. If I have log base a of a to the x, that's equal to x. And if I have a raised to the log base a of x, that's also equal to x, right? It's not all these properties extends to logs of other bases. And exponentials of other bases as well, right? It doesn't have to be base E. It can be other bases as long as they match, right? So log base A with an exponential base A, exponential base A with log base A, they're all going to work the same way as base E. I'm just go ahead and just spell out all the two new rules that we're going to have to know beyond natural log and exponential. But I'm going to kind of organize it in a way where you can see the connection between them. And so even though these are new rules, we can kind of feel it kind of feels more like, oh, I'm just adding on to the parent rules that we already know. So let me just create this chart here. Let's say we have the two rules that we already know, the two new rules, the two more important rules, right? And we also learned this rule here. Now, these are really nice and clean. This is a base E, so base E's derivative is just going to work out a little nicer. But let's say we're talking about base 2 or base 3 or base 5, natural or log base 2 or an exponential function base 2 to the x. The rules will follow a similar pattern, but there's a little bit extra that needs to be involved. So one of the rules is this: if I have the derivative of, let's say this is log base E, that's it's going to have a nice clean rule. But what if it was log base 2 or log base 3 or log base 4? We use log base A to represent any other bases. Okay, so if it's any other base, it's still u prime over u. Okay, so put that at the end, but there's something in front. So I want to just show that we still u prime over u, but there's a conversion that has to happen. It needs to convert into base E before it turns into that nice u prime over u. So to convert to that base E, there's a coefficient, a 1 over natural log of A, that has to live in front of that variable. Sorry, in front of that derivative. Okay, we'll practice this. Okay, but hopefully we see that connection, right? Okay, log base E, log base A, they both are u prime over u, but if it's log base A, it's not as clean. There's a little bit of adjustment that needs to be made. Okay. Yeah. These are the important ones, okay, but hopefully we memorize this and we can just adapt to know these other ones as well. Okay, you'll have to know these for the quiz, but chances are these have a higher chance of showing up on the AP exam than these right here. Okay. All right, so derivative of A to the U. So this is base 2 or base 3 or base 4. All of them can be grouped together into this base A. So we know the derivative for e to the u is just the original function times the exponent's derivative. The same thing is going to apply here, but there's something in front. So I'm going to leave a little space. I want to show you that we're going to essentially follow the same pattern as e to the u. So it's still the original function times the exponent's derivative. But there's a little bit of a bit extra. So that extra is a conversion that has to happen. So that conversion is just simply natural log of A. So it's just a number that has to sit in front of my derivative. Just like over here, a number that has to sit in front of my derivative. Okay, so we're going to practice with these two rules today. All right. We're going to focus first on this rule here. Okay, so example 3. F of x equals log base 5. Log base 5, this is similar to natural log, but this is not base E, this is base 5. Now, once I'm in a log expression, all the properties that I use with natural log also extends to logs of other bases. So product property, quotient property, power property, they all work with other bases as well.
Probably we did earlier, right? It's like the 4 squares.
Yep.
It's like...
Oh, no, sorry. Yeah, this is different. This is, I know it looks similar, but before I was using the 4 squares as for inverse functions, how we're kind of working the derivative Sorry, this is just to show that these are related, and I just want to show that connection. Yeah, so no connection with the derivative inverse. Okay, so here, if I have log base 5 of cube root of 2x squared plus 7, imagine this is natural log, right? This is natural log. I want to apply log properties. Same thing here. I want to apply log properties before I jump into my derivative. So I'm going to rewrite log base 5. I can write this as a parentheses, so I can raise this expression to what power? To the 1/3. Okay. Just like with natural log, what can I do with this exponent? Bring it down in front, right? It's still, if this is natural log or log, my property still stands. So logs and natural log, they all have a similar derivative rule. We're going to keep that 1/3. We're going to have u prime over u, but there's going to be a little bit that we have to keep track in front. Okay, so this is follow the rule here. Y prime equals 1/3 stays. Log base 5. This is not natural log, so I got to do a little bit of conversion here. There's another coefficient that's going to be in front. 1 over natural log of what? 5. Yep, that's my base. Natural log of 5. So once I get past that messiness, then it feels just like your natural log rule. U prime over u. Okay, what's u prime? Yeah, and this is my u value, right?
4x.
So 4x, yeah, over. Yes. Yeah. The only cleanup that you may have to do is just to try to push it all under one fraction. That's all. Okay, example 4, find f prime for f of x. Now imagine this was natural log. If this was natural log, what would you do before you do your derivative? Quotient property, right? Natural log of a over b is just natural log of a minus natural log of b. Same thing. Log of a over b is log of a minus log of b. Now, we don't see a base here. Do you guys know what that base is? 10. Yeah, so
Base 10.
right. So the two most common bases that we use for logs are base E and base 10. So that's why they have shorthand abbreviations for them. So instead of writing log base E, ln is the notation for that. And instead of using log base 10, they just do log. So if it's logs of other bases like 2, 3, 5, or 7, they have to indicate that. But if they leave a number out, just understand that's a 10. Okay, but we can apply using log properties first. Quotient property, we're going to break this u value into easier u values. But I'm going to put a 10 here just so we can see it more clearly. Okay, so this is still, I'm still at the function level, haven't done anything with the derivative. Is there anything else I can do to make life easier before my derivative step comes in? Yeah, let's move that 3. I wouldn't move this 3 here. This 3, I mean, if I want to move that 3, I got to separate the 5 and x cubed. That's too much trouble.
Use it in purposes.
Yeah. Well, also the right. You're right. It's in the if the cube was outside the parentheses, then I can bring that down. But these are two separate terms. I'll have to separate these first and then bring the 3 down. And that's too much trouble because this u value is already pretty manageable, right? That's not a difficult u value. But this one, prefer not to go through a whole chain rule. Bring that 3 down. So we're still at the function level. It's going to copy everything else down here. Okay, so now we can apply our derivative rule. Basically, it's just u prime over u with a little bit of conversion that has to happen. So the conversion is 1 over natural log of a. That sits in front of u. Yeah, 1 natural log of 10. That's just the number. That's just the coefficient. That's going to go in front of my true derivative, u prime over u. Okay, what's my u prime? Over 5x cubed. Okay. Basically, u prime over u with that conversion and the coefficient. So I just have to put all three together. Okay, u prime over u.
We do have to include the 10, even though it's not there. You still have to include.
Well, it's not showing up in a notation, but it will show up in your derivative. Right. So if it helps, whenever you don't see a 10 there, put a 10 there, and that way you can build out everything and see that 10 and work in the 10 into your derivative. And I can do some cleanup within each fraction here. Sorry, 3. 3 over 15 over 5 reduced to be just 3 over 1, right? So 3. Minus 3 times 2. Okay, so I just want us to think of this. Okay, this is treat it like a natural log problem. Just know that when you come to the derivative portion of it, we just have to include a little bit more extra into our derivative rule. But if we think of it as just an extension of the natural log rule, then it doesn't feel like something completely new, right? It feels like something that is the same process. We just have to include something extra with that additional, that change in base. Okay, next page. Let's work on some exponential functions that are not base e. Exponential function that could be other bases like base 2 raised to the x, base 3 to the x, base 5 to the x. So here's our rule. If I have base a to the u, I do natural log of a times a to the u times u prime. So example 5 is an instance of that. We have to be able to recognize the different families of functions, right? This is not power rule. This is not a variable raised to a variable. This is a constant raised to a variable. This falls under an exponential function, right? We have to recognize this as an exponential function. And then we can apply accordingly, right? We'll treat this like e to the u. We follow pretty much the same rule as e to the u, with just a little bit of conversion that has to happen in front, right? The rule for e to the u is just the original function times the exponent's derivative. Same thing here. Your original function will show up in your derivative times u prime with a little bit of extra. Okay, so I'll write the rule in front and we'll apply it. Okay, no need to rewrite anything. We can't expand anything. We have to jump directly into our derivative. Okay, so y prime equals. Just like, let's see, what do we start off with? What's my a value? 5. So natural log of 5, there's that conversion that has to occur first. Then the original function is going to show up. What's that? Times u prime times the exponent's derivative. Yeah, we do need to put it in a set of parentheses to kind of section it off a bit. but there's not much that we can clean up. Rearranging doesn't really help it at all. This is it. Leave it alone. This is our derivative.
That's it.
Mhm.
Do you separate the U value? You bring it to in front.
I'm just following what this rule says, right? So rule says natural log of a, my a is 5, my u is x squared minus 2x. So natural log of 5 times 5 to the x squared minus 2x times u prime. U prime is the derivative of that exponent, so 2x minus 2. Oh, what was your question?
Oh, no, I was wondering, obviously, you just separate the 2x minus 2 to the derivative U.
Right, yeah, I want that u prime to sit separate from this expression. So if I didn't have the parentheses there, then it may be interpreted as 2x minus, this whole thing minus 2, which is not true. So I just want that u prime to be by itself.
Would there ever be a case where you can simplify that down further?
Not much, yeah. With exponential functions, these are all kind of its own thing. Natural log is its own thing. Exponential is its own thing. 2x minus 2 is its own thing. It's hard to clean this up.
And A will always be like the
Yeah, a is always, the natural log of a can never combine into something else. It kind of has to stay there, right? Yeah, we're gonna see. Yeah, these derivatives, it's not hard. It just looks messy. It feels like we should clean things up a bit, but there's not much that we can do with all these different families that are all showing up at the same time. Okay, all right. Example 6. F of x equals x to the 4 to the x times 4 to the negative x. Obviously, there's an exponential function here. We got to apply that a to the u rule. But do you see something else that we have to involve here? Product rule. Do you see how x and 4 to the negative x are being multiplied? They're different terms. And if I'm involving a derivative with terms multiplied, I got to go through product rule, right? Okay, f prime, x becomes my g function is the original. Back to f. And g prime, so now I've got to approach the rule for a to the u. So 4 to the negative x starts off with what? Yep, natural log of 4 times that's -1. Yep. Do a little bit of cleanup here. 4 to the negative x, I can rewrite as 1 over 4 to the x. I can drag that negative in front. The natural log of 4 can stay above. I can bring that 4 to the negative x to the denominator. It's already sharing a common denominator, so I can just make it into the same fraction without too much effort. Yeah. Oh, the -1. I'm just following the rule here. So natural log of 4 times 4 to the negative x times u prime. So what's negative x's derivative? -1. Yeah. So my exponent's derivative is staying here. We'll skip example 7 for now, but I want to use this space to kind of clarify the different rules involving X, because sometimes we look at a problem and we may not know which category we're dealing with because they all look similar. So I want to kind of point out especially 3 similarities. So I want to split this up into 3 sections here. Now, these all look similar. These all involve X and 2, but depending on where your variable is sitting and where your constant is sitting, we have completely different rules that apply for each situation. Let's start with this one. If I have a variable raised to a constant, what rule is this? This is power rule, right? So power rule, y prime is just what? 2x, right? This is the easiest one, right? But I don't want us to confuse this with other rules because other rules may look similar, but it doesn't, we don't apply power rule unless it's a variable raised to a constant. Right? This one, 2 to the x, this falls under which category? What type of function is this? This is an exponential function. So exponential function has its own rule, right? The one that we just did above. So y prime is natural log of a times a to the u, the original function, times u prime. So if I have a constant raised to a variable, that's an exponential function. This one here is what? A variable raised to a what? Variable. Variable raised to a variable. We don't have a rule for this. Okay. So this we have to rewrite using log differentiation. So this one is the one that is the most difficult to recognize and apply because we have to apply using log differentiation. So the whole idea with log differentiation is we introduce logs into the problem to allow for that 2x to live somewhere else so that we're not forced to deal with a variable raised to a variable because we don't have a rule for that. So let's work through this problem. First, we introduce natural logs into the problem. Now this opens up some possibilities, right? Now that I'm inside a log expression, where can that exponent go? To the front. But when it comes out to the front, it turns into a multiplication problem, which means that if I want to find the derivative, I got to go through what? Product rule. Yeah, so anytime there's log differentiation with this setup, you're always going to be expecting product rule when we get to this portion. Okay, so now we're ready for the derivative. Natural log of y, a little bit of implicit. What's the derivative of natural log of y? 1 over y, right? We find the derivative first. Natural log of u is u prime over u. So 1 over y, then we attach dy dx. And then we got to go through product rule, right? So f prime g plus f g prime. Okay, 2x becomes 2. G, no changes. Back to f. And g prime is 1 over x. Okay, we're trying to solve for dy dx, which is the same thing as y prime. But how do we get this by itself? Right. So dividing by 1 over y is the same thing as multiplying by its reciprocal. Right? I'm gonna buy myself more room here. Now we started off with a function, which means that this y is only a temporary variable. I should be able to represent my answer purely in terms of x. So what can I replace this y with? The original function. Two x over x is just 2. So I want to make sure that we can distinguish between these three and that we don't confuse one for the other, even though they kind of all look similar. So variable raised to a constant is power rule. A constant raised to a variable is exponential. A variable raised to a variable, we don't have a rule. We're forced to use log differentiation. Okay, your homework is page 21. We have 15 minutes. We can get started with that. So go to page 21.
Whole page, right?
Yeah, whole page. Yeah, but I think we should be able to get through at least half of it by the end of class. I do want to point out something else about rules here. When memorizing rules, tendency is we know there's natural log of a involved, but sometimes we get confused as to wait, where does it go? Does it go in the denominator or the numerator? So the way that I remember it is my natural log has u prime over u, right? So if there's a denominator in my original derivative, that helps me remember that the natural log of a goes in the denominator. Okay. My exponential function has no denominator at all within its derivative, so that helps me remind me, oh, that natural log of a is going to go in the numerator. So that helps me remember where the natural log of a goes, right? One goes in the numerator, one goes in the denominator. So that u prime over u, that u denominator reminds me, oh, my natural log of a is going to go in the denominator as well.
So, oh, U has a denominator?
Hmm?
So if U has a denominator, then U has the bottom first.
Right. So if because sometimes students feel like they don't know where that natural log of a goes. They go to the numerator or does it go to the denominator? So for logs, it goes in the denominator because there's a denominator within my derivative. So if I just remember my natural log and exponential rule, there's a denominator here. So with logs, there's a natural log of my derivative. There is no denominator. So therefore, the adjusted a to the u also has no denominator. Okay, so let's start off page 21. These are rules that we can simply apply by using a to the u rule, right? Natural log of a times a to the u times u prime. Follow what the rule says here. Natural log of 5 times 5 to the negative 4x times negative 4. Okay, great. Gotcha. Thanks. Okay, 3940 should feel pretty straightforward. Again, we need to be able to recognize oh, this is exponential function. I gotta do a to the u, right? So I do see students treating this like power rule, and they'll bring down negative 4x and they'll do negative 4x minus 1. So this is not power rule, right? We got to go through this its own exponential rule. 41 and 42, can you recognize what else is needed besides exponential rule? Product rule, right? So hopefully we've seen enough now where we can recognize, oh wait, this is product rule. I got to apply product rule here. Those are not the same expression. They're being multiplied. They're separate. Yeah, and with these, there's not much to do with cleanup. I'm not gonna ask you to do much cleanup here. You have exponential, you have x, you have natural log showing up. It's just going to look messy. Okay, 49 and 40. Yeah, the second half, they all involve logs. So just pretend like you're looking at natural log and pretend you're just looking to clean up your log expression just like your natural log, right? So look for opportunities to apply log properties such as product property, quotient property, and power property. Doesn't mean that it can always apply, but we always want to look for it, right? It can simplify our log problem just like how it simplifies our natural log problem.
Oh, it's 1, 2.
Yeah.
And once you put the terms together.
Yeah, we really can't do much there. I mean, you can factor out the GCF, but I'm not going to ask you to do that. So yeah, that's good enough.
Could you like put the terms together and multiply?
You could, yeah, you can put the X closer, but not much else. Okay. 49. Can we do any cleanup with 49? Yeah, bring that exponent down. Good. Can I do any cleanup with 48? No. Okay, we can't distribute a log base 3 through. And also, that's not a difficult U value, right? So we can jump directly into our derivative rule. So treat log base 5 and log base 3 as natural log is still U prime over U, but with just a little bit of coefficient extra that has to live in front of your derivative. So 49, you're going to have a 1 over natural log of 5 that shows up. For 48, you'll have a 1 over natural log of 3 that shows up, but it's still U prime over U. So whenever I see an exponential function, I'm always thinking to myself, okay, how do I handle e to the u? And that's how I handle a lot very similar how I handle A. Log base 3, this looks more intimidating than natural log, but just treat it like a natural log problem. And then really, this is the only thing that's different about this versus natural log, right? So hopefully we feel pretty good about natural log. This is just a slight extension for other bases.
48 is y prime, right?
Yes, sorry, y prime. It's there, it just disappeared, it just didn't show up that well.
Also, so 49, like you bring the two all the way over to the beginning of the expression, not for being purposes.
Exactly, right. It needs to be in front of the outside the expression. Yeah. Yeah. Yeah, it comes all the way down in front, right? Okay. Number 50, is there anything that we can do before we jump into our derivative?
Bring the 3 over.
Yeah, the 3 for 50, how about for 51?
Bring the 1/2 into it.
Yeah, write it as 1/2, then bring that 1/2 down, and then your derivative should feel pretty straightforward after that. Right, take a look at 53. What can we do before our derivative step? Expand it, yep. Just like how you would expand natural log, you can expand it the same way with log base 2. Split it up into 2 problems, and then your derivative will feel easier. 52, write that as parentheses raised to what power? 1/3, yeah. Then it feels just like 51, right?
What would you just do with that?
So I would continue splitting up. So I can use product property. Log of A times B is log of A plus log of B. All right, take a look at 55. 55 has 3 parts, right? So imagine I gave you natural log of AB over C. How would you expand natural log of AB over C? Yep, so you can apply this process to 55, right? You got your A and B and your C below. What if I had natural log of A over BC? What would this look like? Yeah, so anything that is living above is part of a positive natural log or log. Anything that lives below is part of a negative natural log. So if this works for natural log, that application can also work for logs of the bases.
And the derivative for 55, like for the 2, it would be 0.
Right, log base 2 is just a number, so.
So would the whole thing be 0 at the end? If we just go. Yeah.
Yes, that's right. That last term will just go away, right? Okay, I'll send out the key this afternoon. If you guys haven't already finished this, so this is the homework I'll be checking tomorrow, and we can start our quiz review tomorrow as well. We have a lot of time to do quiz review, so that's good. But you know, there's a lot of rules to go through, so it's good to have a lot of time to practice through it. Okay, come get your phones. Almost you. Thank you. No, that's second. That's good with carrots. It's like my whole time. Show everything. Put it. What? It's. Not used to be like so.
Two jobs, you get a So, yeah, just do it, and then you get a attention on everyone else around. But I'm doing under the price. It's just your job. It's like, sorry, guys. You're just right, bro.
They said you just like sense like.
Not the first period. It was the first. Not first.
Good. How are you?
Pretty good.
The whole Birmingham Falls Highway was backed up.
How do you feel about the Bears?
Like, I couldn't even get out of my.
How do you feel about it? If you go make a comeback?